Good morning, everyone. Today, I would like to share the main message of a book entitled Designing Infrastructure for Uncertain Ground, Geology-Aware Engineering for Safer Megaprojects, by Andy Andriancia. The book addresses a problem that every major infrastructure project must face, but that is often underestimated. We never know the ground completely. When we design a tunnel, bridge, dam, highway, foundation, or major underground structure, we rely on geological investigations, boreholes, laboratory tests, geophysical surveys, maps, models, and engineering calculations. But the structure does not interact with our drawings or models. It interacts with the real ground. And the real ground can be different from what we expected. That difference is geological uncertainty. The central message of the book is simple. We cannot eliminate geological uncertainty, but we can design the engineering process so that uncertainty is identified, communicated, monitored, and managed. This is the foundation of what the book calls Geology-Aware Infrastructure Design, or GAIDF. Let me explain the idea step by step. Why does geology matter? Infrastructure failures are often described as structural or construction failures. But many serious failures begin with a mismatch between assumed and actual ground conditions. The problem is not necessarily insufficient calculation. Sometimes the calculations are technically excellent. The problem is that those calculations may be based on an incomplete or incorrect representation of the ground. A geological model is always a representation. It is never the ground itself. The book identifies several sources of uncertainty. There is natural variability, because geological materials are heterogeneous. There is model uncertainty, because we simplify complex geological systems into engineering models. And there is epistemic uncertainty, things we simply do not know yet, some of which can be reduced through additional investigation. The important point is that uncertainty is not abnormal. It is a permanent characteristic of infrastructure engineering. Therefore, the first principle is: do not design as if the ground were completely known. Design with uncertainty in mind. Investigation as hypothesis testing. The book argues that geological investigation should not simply be treated as data collection. It should be treated as hypothesis testing. Before drilling another borehole or commissioning another survey, we should ask: what do we currently believe about the geology? What are the most important uncertainties? Which uncertainty could actually change our engineering decision? And what investigation would reduce that uncertainty? This changes the philosophy of site investigation. Instead of asking, how many boreholes should we drill? We should ask, what information do we need to make a better decision? The book discusses desk studies, remote sensing, geological mapping, boreholes, core logging, geophysical investigation, and hydrogeological monitoring. But the most important message is integration. Geophysical data should be calibrated against borehole information. Borehole spacing should reflect the scale of geological features that could affect the project. Groundwater monitoring should begin early enough to capture changes over time. One investigation campaign cannot tell us everything. The book highlights three fundamental limitations. First is the geometry problem. We sample only a small portion of the underground volume, while most of the ground between investigation points must be inferred. Second is the temporal problem. Groundwater levels, pore pressures, and other conditions can change with rainfall, seasons, construction activities, and regional conditions. A borehole investigation is often only a snapshot in time. Third is the testing problem. Laboratory and small-scale tests cannot perfectly reproduce the behavior of a large, heterogeneous geological mass. Therefore, good investigation should communicate not only what we know, but also what we do not know. Communicating and managing uncertainty. A good geological report should communicate uncertainty rather than hide it. Design teams should understand alternative geological scenarios, parameter ranges, confidence levels, spatial uncertainty, and residual uncertainty. The book also gives importance to the Geotechnical Baseline Report, or GBR. The GBR is not merely a technical document. It can also influence how geological risk is allocated between the project owner and contractor. Another important concept is the observational method. We may not be able to predict the ground perfectly before construction. Instead, we establish a most probable condition, evaluate an adverse but plausible condition, prepare contingency designs, and install monitoring systems capable of detecting deviations. In other words, we do not simply predict. We predict, observe, compare, and respond. Uncertainty in engineering models. A single geological interpretation or parameter value is often not enough. Geological and geotechnical parameters should be treated as uncertain quantities using ranges, probability distributions, coefficients of variation, correlations, and scenario analysis where appropriate. Tools such as Monte Carlo simulation can help propagate uncertainty through engineering calculations. Random field theory can represent spatial variability. Bayesian updating can combine existing knowledge with new information. But technology is not the main point. The main point is that the engineering model should reflect the uncertainty that actually matters, and it should be updated when new evidence becomes available. This is where monitoring becomes essential. Monitoring is not simply about alarms. It should test whether our assumptions are correct. If predicted settlement differs from observed settlement, that difference is information. If tunnel convergence falls outside the expected range, that is information. If groundwater pressure behaves differently from the model, that is information. We should then ask, why is the ground behaving differently? Does this indicate a geological feature that was not captured? Does the engineering model need to be updated? Does the design need to change? This is the feedback loop. Applications to infrastructure. For foundations, performance depends on more than nominal bearing capacity. We must consider spatial variability, bearing stratum continuity, settlement, groundwater, scour, cavities, and construction variability. Karst terrain is an important example. A cavity may exist between investigation points and remain undetected. Therefore, in cavity-prone geology, the investigation and foundation system should be designed around the possibility of voids rather than treating them as exceptional surprises. Geophysical surveys, probe drilling, inspection, grouting, confirmation drilling, and pile integrity testing can form part of a systematic approach. Ground improvement is also geology-dependent. Methods such as preloading, vertical drains, vibrocompaction, deep mixing, grouting, dynamic compaction, and stone columns can be effective in the right geological conditions. But a method that performs well in one geological environment may perform poorly in another. That is why pilot-scale trials are valuable. Before full-scale treatment, we should verify that the method actually works in the project's geology. Now consider tunnels. A tunnel is unique because construction itself becomes a geological investigation. The excavation phase reveals information that was not available during the original investigation. Therefore, tunnel engineering must be adaptive. Rock mass classification systems are useful, but they should not replace geological understanding. Fault zones, fractured rock, weak zones, groundwater, squeezing ground, and mixed face conditions may require different responses. The support system should therefore be capable of adjustment, with monitoring connected to predefined trigger levels and actions. Again, observe the ground, compare it with the model, and respond before the situation becomes an emergency. The same logic applies to slopes and landslides. Geology should come before calculation. A sophisticated slope stability analysis is not useful if the assumed failure mechanism is wrong. We need to understand structural geology, discontinuities, groundwater, previous landslide surfaces, weathering, and geomorphology. Technologies such as LiDAR and NSAR can help identify large-scale deformation and geological features, but the data still requires geological interpretation. Adaptive construction. One of the strongest messages in the book is that flexibility must be designed before construction starts. It cannot be improvised effectively when the project is already under pressure. Construction should include formal hold points where geological observations and monitoring data are reviewed before the next stage is authorized. Flexible systems such as variable support classes, bolt density, shotcrete quantities, or pile lengths allow the project to respond to actual ground conditions without redesigning the entire system. Contracts also need to reflect geological variability. Unit rate items, provisional sums, and changed condition mechanisms can provide structured ways to manage geological uncertainty. This is not about creating excuses for poor performance. It is about recognizing that legitimate geological variability is a technical reality. Digital technology and AI. The book also explores digital twins, real-time monitoring, 3D geological models, BIM integration, distributed fiber optic sensing, automated total stations, NSAR, machine learning anomaly detection, and robotic inspection. These technologies can transform how geological information is managed. But there is an important distinction. Raw monitoring data is not the same as engineering intelligence. A dashboard may show thousands of sensor measurements. But engineers need to know: what geological feature does the sensor represent? What behavior did the design predict? Is the measurement within the expected range? And what should we do if it is not? A useful digital system therefore connects sensors with geological models, engineering predictions, and decision rules. This is the role of the digital twin. It is not simply a three-dimensional picture. It is a dynamic representation of the infrastructure and its geological environment, continuously updated with new information. The book takes a balanced position on artificial intelligence. AI can be powerful for pattern recognition, anomaly detection, classification, and predictive analysis. But AI does not eliminate the need for engineering judgment. Geotechnical engineering depends heavily on geological context, spatial reasoning, uncertainty, and understanding of geological processes. Therefore, the book advocates human-AI collaboration. AI can process large amounts of information, while engineers and geologists remain responsible for interpretation, validation, context, and decisions. Climate-aware infrastructure. The same principle applies to climate-aware infrastructure. An infrastructure asset may operate for decades, while its geological environment and boundary conditions change over time. Rainfall patterns, groundwater, sea levels, temperature, and other environmental conditions can affect long-term geotechnical performance. Therefore, infrastructure should not be designed only around historical conditions. It should consider the conditions under which the asset is expected to operate throughout its life. The GAIDF framework. So, what is GAIDF? The Geology-Aware Infrastructure Design Framework brings these ideas together through 6 components. 1. Strategic geological investigation. 2. Subsurface uncertainty modeling. 3. Risk-based engineering design. 4. Adaptive construction planning. 5. Monitoring and feedback systems. 6. Geological risk governance. These 6 components form a lifecycle. Investigation informs the geological model. The model informs risk-based design. The design informs construction. Construction generates observations. Monitoring captures performance. And those observations feed back into the geological model. That reverse flow is essential. The project learns from the ground. This is perhaps the most important conceptual contribution of the book. Traditional engineering often follows a linear path. Investigate, design, build, operate. GAIDF adds a feedback loop. Investigate, model, design, build, monitor, learn, update. The difference may sound small, but it fundamentally changes how projects deal with uncertainty. Instead of treating unexpected geological conditions as failures of prediction, the project is designed to learn from those conditions and respond systematically. Practical message for infrastructure leaders. The practical message is clear. First, establish a conceptual geological model before committing to detailed investigation. Second, identify uncertainties that can actually change decisions. Third, investigate those uncertainties deliberately. Fourth, carry uncertainty into the engineering model. 5th, evaluate adverse but plausible scenarios. 6th, prepare contingency designs before they are needed. 7th, make construction flexible enough to respond to actual conditions. 8th, design monitoring around specific failure mechanisms. 9th, connect trigger levels to clear actions and responsibilities. 10th, use construction and operational data to update the model. And finally, preserve geological knowledge for future maintenance and adaptation. Closing. Let me close with the central idea of the book. The ground is uncertain. That fact cannot be changed. But the engineering process does not have to be uncertain. We can investigate strategically. We can communicate what we know and what we do not know. We can model uncertainty rather than hide it. We can design for plausible variation. We can prepare contingencies. We can monitor performance. We can learn from construction. And we can continuously update our understanding. The goal is not to predict the ground perfectly. The goal is to build infrastructure that remains safe, resilient, and manageable even when the ground is different from what we expected. That is the essence of geology-aware engineering. And that is the central message of designing infrastructure for uncertain ground. Thank you.